The second law of thermodynamics, entropy. There are three factors that determine if a reaction is spontaneous. The relative role of each will become clearer as we proceed. Change in enthalpy, change in entropy, and temperature. Enthalpy and temperature have already been studied. Entropy is defined by the second law of thermodynamics. A key element, along with the change in enthalpy and temperature in determining if a reaction is spontaneous, is the change in entropy. The symbol for entropy is capital S. Entropy can be thought of in a number of ways that upon close examination prove to be equivalent. First one, as a measure of the number of energetically equivalent ways a system can be arranged, as a measure of disorder in a system, and finally, as a measure of the degree to which energy has been dispersed and unable to do work. Heat transfer from a hot object to its cooler surroundings is spontaneous, primarily due to the increase in entropy. When a hot pan cools to room temperature, thermal energy that was initially concentrated in the pan becomes dispersed throughout the room. This represents a dispersal of energy over a greater number of particles and increase in entropy without a change in energy. When energy is dispersed over a greater number of particles, there are more ways the energy can be distributed between those particles. Now let's look at an example to see how our three perspectives of entropy, these three which we just showed, are equivalent. We'll assume we have three particles, A, B, and C, which together have 3 units of energy, represented by 3 asterisks, right here. We'll determine how that energy can be distributed between those particles in 2 different scenarios. The first will isolate each particle so it can have no reactions, no interference with the other particles. So you have 3 states. You can either have all the energy here, all the energy with B, or all the energy with C. But if they're in contact, there are 7 possibilities for energy to be spread out over them. They can each just take 1 unit. You can have 0 units, 1 unit and 2, and then etc. Right? You've got all these different ways to split that energy up. The 7 states of the second scenario show higher entropy by each of our definitions. We have more energetically equal ways the system can be arranged. Right? Each case, they have 3 asterisks of energy. There's more disorder. And finally, the energy is dispersed over different objects, and it spreads out. When particles expand to occupy a bigger volume, there is a dispersal of energy and therefore an increase in entropy. Have the solid here, here's liquid, and here's gas. As the substance changes from a solid to a liquid to a gas, the energy of its particles becomes more dispersed, as they have more space in which to move and more ways in which they can move. Right? The solid, they're all locked into those positions. The liquid spreads out a bit more. And finally, in a gas, they're maximally spread out. When a valve is open between these 2 flasks, you have one flask that has nothing in it, it's a vacuum. And over here, you have bromine gas. So when you open the valve, the bromine gas flows over here. So the gas that was initially only in flask B is now in flask A and B. By spreading evenly between the 2 flasks, the matter and energy of the gas is dispersed. The entropy increases, so this process is spontaneous. Also, the temperature of the gas would be the same in both flasks, since that represents the greatest dispersal of energy, or the highest entropy. So it's spontaneous going this way, where you now have half an atmosphere pressure in each one, where before you had 1 atmosphere and 0 pressure, right? It was a vacuum. This has higher entropy and is spontaneous. The gas then will not go back without doing extra work on it in that direction to put all the gas over in B and have nothing in A. That just won't happen. So the question that was actually just answered, will bromine ever spontaneously move from flasks A and B into just B? So will it ever go this way? Gas coming here, and then it all gets concentrated back in B. The answer is it's not thermodynamically favorable because it would bring about a decrease in entropy. This is an example of a process that can only be reversed by doing work on the system to compress all this gas here, maybe put a big fan there, and blow it all back into B. James Clerk Maxwell, the same scientist who devised the Maxwell's equations which explained electromagnetic theory, devised a thought experiment that would break the second law of thermodynamics. In the thought experiment, a gas occupies the entire volume of a container, over here. A massless door, right here, separates the container into two chambers, A and B. A demon, hence the name Maxwell's demon, controls the door in such a way that only the faster moving particles, the red particles, pass into one of the chambers, and only the slower moving particles, blue, pass into the other chamber. So here's all the blue coming over here, and all the red, the faster moving ones, going over there, controlled by this guy here. This would bring all the warmer particles to one side of the door and the cooler ones to the others, without doing any work. The energy would be less dispersed. That means entropy would be decreased and the second law violated. Scientists continue to study this idea in theoretical discussions and experiments, though all proposals have been proven theoretically impossible. Work would be required. And who's doing the work? The demon here. Take the demon out and this wouldn't occur. No one has ever demonstrated a violation of the second law of thermodynamics. Since processes that increase entropy are often spontaneous, it's useful to recognize scenarios that increase or decrease entropy. Gases have more entropy than liquids. Liquid particles have some order to their arrangements due to the intermolecular attractions. Processes that increase the number of moles of gas also increase entropy. Liquids have more entropy than solids. So let's just underline that. Solid particles are not able to rearrange themselves, making them highly ordered. Melting a solid will therefore increase entropy. You're going from solid to liquid. Dissolving a solute in a solvent increases entropy, since the dissolution process involves a dispersal of particles. Keep in mind that entropy is not the only determining factor in evaluating whether a process is spontaneous or not spontaneous. Just as enthalpy doesn't give the whole picture, neither does entropy. So we're going to have to relate them, won't we? To predict whether entropy increases or decreases during a reaction, in other words, this means the entropy change in the system is what we're looking for. First, we'll compare the phases of the reactants and the products. So we will have an increase in entropy during vaporization, when you go from a liquid to a gas, during sublimation, a solid to a gas, or melting, solid to liquid, all increases in entropy. A decrease in entropy happens during condensation, where you go from a gas to a liquid, deposition, gas to a solid, or freezing, liquid to a solid. Next, look at whether the number of gas moles, not solid, not liquid, is increasing or decreasing during the reaction. So the first one here, we have 2 gas moles in the beginning, and we wind up with 2 plus 3, that's 5, so that is an increase in entropy. Decrease in entropy. We have 2 plus 1, that's 3, 2. We've got the number of gas moles decreasing, entropy decreases, and here 2 moles on that side of hydrogen and chlorine gas, and 2 moles on the right side. So that is a negligible change in entropy. Finally, is one substance dissolving in a solvent or precipitating from a solvent? So the first case here, increase in entropy. Why? Because the sodium bromide is dissolving in a solution, goes from a solid to aqueous. Second one, decrease in entropy. We're precipitating out silver chloride. Third, entropy is increasing. We have carbon dioxide is leaving solution and going into a gaseous form. And finally, a decrease in entropy. We have oxygen dissolving in a solvent. Let's work through some problems where we will predict the change in entropy. We have a pinch of salt dissolving, potassium chlorate turning into potassium chloride and oxygen. A gas gets concentrated more in one part. We have hydrogen chloride plus ammonia turning into ammonium chloride. Ice melts at room temperature, and a hot cup of coffee warms while sitting at room temperature. For the salt process, we have an increase in entropy. The dissolution of a solute in a solvent causes a dispersal of particles, leading to increased disorder. The particles of mixtures have a less ordered arrangement than those of the pure substance, so entropy goes up. Second reaction, potassium chlorate. This process has an increase of entropy. There are more moles of gas on the product side of the reaction. There's going to be 2 plus 3, 5 moles, and here you have 0 moles. It's a solid. Gases have more entropy than solids or liquids. For the gas concentrating, we have a decrease in entropy. The more the particles of a substance spread out, the greater the entropy. Similar to compressing a gas, concentrating the particles in a smaller volume makes the arrangement of particles more orderly, meaning there is less entropy. So entropy goes down. And the last one here, we've got hydrogen chloride a gas, ammonia a gas, turning into a solid here, ammonium chloride. This has a decrease in entropy. There are more moles of gas on the reactant side, right? You have 2 moles here and 0 over here. Remember, we don't deal with the solid. We're just talking about moles of gases. So we have a greater entropy, and what's going on here? The entropy is decreasing. Ice melts at room temperature. This process has an increase in entropy. Liquids have more entropy than solids. Entropy goes up. A hot cup of coffee warms while sitting at room temperature. This one's a little tricky because you look at this. Warms typically means something is getting hotter, in which case you would have an increase in entropy. But the key is it's sitting at room temperature. So what's really happening is the temperature is going down. So that means the process has a decrease in entropy. Energy becoming more concentrated in a small area would cause the energy to have less dispersion. The second law of thermodynamics states that for any reversible process, the change in the entropy of the universe is 0. Delta S is equal to 0. For any irreversible process, the entropy of the universe increases. Delta S is greater than 0. And we'll be using words like change in entropy, delta S greater than 0, delta S less than 0, delta S equal to 0, all interchangeably. Spontaneous processes are irreversible, so for those, delta S is greater than 0. Just as for the total energy of the universe, it is useful to divide the entropy of the universe between the system and its surroundings. So we have the change in entropy of the universe is equal to the change in entropy of a system, however you describe it, plus the change in entropy of everything else in the universe. Contrast this with the first law of thermodynamics, which requires that the total energy of the universe is constant. To predict whether a reaction is spontaneous, we must know the sign, positive, negative, or 0, of delta S universe. If the change in entropy of the universe is positive, the reaction is spontaneous. If delta S universe is negative, it's non-spontaneous. If it's 0, the reaction could occur in either direction. To predict whether a reaction is spontaneous, the entropy changes in the system and the surroundings, right, because they have to add up to delta S universe, must be determined separately and then summed.